Welcome. Got kind of two things going on here. All right, so I just wanted to point out a few things, some important things that I will put in. I'll put the due dates in our notes as well when we go to the notes. But first thing I wanted to show you, I posted some tables. I'm not going to hit it because I'm worried that it's going to be, okay, I'm going to hit it. Okay, it wasn't too slow. So here you have some Z tables and of course the T tables that we talked about last day. So if you need the tables, then here's a set of tables. You can easily just Google them, but it's nice to have in case you need them, right? Mostly for critical values, right? For making confidence intervals, but I'm going to show you how to make a confidence interval using R. And I found this one. So this link has a really nice look and feel, I think. And so it's really useful. So for each of the things, so here are some key kind of introductory statistics, things that you may or may not know already, right? So for example, what I'm stealing from is maybe I stole it from here, right? But calculating confidence intervals in R. So he's got this nice little video here that you could watch if you want to. And then if you are interested in what's going on, right, the calculation that we're doing, then he's got that here. And then he just kind of talks you through and then walks you through some of this code. There's lots and lots of different ways that we can do things. And so the more we see, the more we know, right? And kind of cute because at the bottom, he has these now you try. So you can type in our code there and it'll run it and you can see what happens. So pretty cool. And so it's got things like one sample t-test in R, two sample t-test in R, 1 and 2 proportion tests, right? Matched pairs. These should all be familiar from stat. Probably 230 or whatever stats you took. But if you're taking it with me right now, then we'll see it in way more detail. But it's nice to have this here. I posted it on our Stat 230 page as well. So it's just nice to have a nice quick summary of all these things, right? And so pretty neat. Let's see if I can close that up so it doesn't slow us down. All right. Now let me scroll down. I posted all those assignments, right? Pretty cute, the big 3, called it in the chat. So the first presentation, I posted a Dropbox for the report and the appendices, and then here's a Dropbox for the first presentation. And it's going to be due next Wednesday, November 10th. Okay, obviously at 11:59 p.m. All my due dates are always 11:59, so I didn't even say that there, but you can click on it and see when the exact due date is. But so that first presentation is due November 10th, and then the chapter 5 and chapter 6 and whatever presentation you decide to do, whether it be on chapter 5 or chapter 6, that's all going to be due November 19th. Okay. So and then I posted the confidence intervals in our code that I want to go through. So I've got that pulled up here. And of course, the PDF that would generate as well. Okay, good. So I'm going to close this so it doesn't slow us down. Hopefully I don't need it. So I tried to keep it as kind of condensed as possible because, like I said, I wanted to show you how to make confidence intervals. But what's nice is we didn't quite finish talking about hypothesis testing. It's supposed to be kind of a review or you know, we're going to talk about it in way more detail in Stat 230. So I just wanted to show you how to make confidence intervals, because that's all you need to know for the Chapter 6 assignment. Okay, so first thing you have to decide is, do you have a mean, right? Are you analyzing a numerical variable or a quantitative variable? Because then you will probably want to talk about the mean, right? And so do you have one sample and you want to analyze the mean? Okay, so to do that, you're going to use a command called t.test. Okay, we know it follows a t-distribution with n-1 degrees of freedom. The t.test actually handles all that, so we don't need to worry about that. All it needs is an x, so that's going to be the x variable. So it's the name of the x column. Okay, and so here, maybe I'll say something, I'll add where x is the name of the column you want to analyze the mean of. Okay. And maybe I'll do these as bullets. Nice, showing off. And mu is the hypothesized value of mu. And to write mu, you can use LaTeX of $/mu. That'll generate a nice looking mu. And here, if it's wrapped up in $, I've just used LaTeX. If you look at the PDF, or if you knit it, you'll see how it generates, right? And it looks nice. So mu is the hypothesized value of mu, and change the confidence level by adjusting level. To generate a confidence interval, we need the alternative to be two-sided, or to be two-dot-sided. Okay, but can also use, oops, can't see anything. Where is it? Oh, can also, now it's, can also use, I think it's like right dot sided or two, what is it? I'll have to have it help me along. So what I do to check it is I do t.test, and doesn't want to help me along. Alternative, how about this? Equals it really doesn't want to help me along today. But can also use just not going to say anything about it. I'll fill it in once I check, but I can't find what the options are. How about this? If I run, I want to know something about the t.test function, I can use a question mark t.test. I'm using the R code chunk as just a little placeholder. I'm going to delete it because if I try to knit it with this question mark t.test, it's not going to work, I don't think. So, but if I run question mark t.test, then we can look at all the arguments. Okay, and so it's two-dot-sided is the default, so we wouldn't actually need to say anything, but we could also use greater or less. So that's what it is. We could also use greater or less for one-sided tests. Okay. So that's a summary of what does it do? So how do we do it? So remember, MT-CARS is just a nice, easy data set to deal with. And so, for example, if we want to answer a question, is there evidence that the average fuel economy, which I'm going to say is the miles per gallon variable, is different from 10? Okay, use the MT-CARS data as your sample. Okay, and assume it's representative of all cars. That's not true, because if we look at the MT-CARS, so if I change my question mark to MT-CARS, pretty sure it was from 1974. Okay. So this is data from cars that are from 1974. So it's not really representative of all cars, but that's what I'm saying. So assume it's representative of all cars. It's not true, but an assumption that we're making. Okay, just to simplify things. Use a 95% confidence interval to support your claim. So if we use a T-dot test, and I'm going to delete this question mark MT-CARS because otherwise it won't work. So T-dot test, here's the variable that I want to analyze. So it'll get all the information that it needs from here, right? It'll get the sample size, it'll have the mean, it'll have the standard error, right? And so it'll have all the information that it needs from just that variable. It then needs to know, well, what do you want me to test this against? And we're saying 10. Is there a evidence of a difference from 10 miles per gallon? We want to make a 95% confidence interval, so we set the level to be 0.95. And then we want the alternative to be two-dot-sided because that's the only way to get a confidence interval. If we use less or greater, it would only give us 1/2 of the interval, so that's not very useful. Notice that because two-dot-sided is text, you're putting it in quotes. That's going to be really important. Otherwise, it's going to complain and it won't work. So then if I run this T-dot test command, I get this output. So it says, okay, I've identified a one sample t-test, and the data I'm using is the miles per gallon. Okay, everything checks out so far. The t that it calculated was 9.471. Fine. That's what we would have found if we had all the information and did it by hand. Degrees of freedom is 31, which means our sample size must be 32, right? And that's correct, so that's good. And then we find our p-value is very, very, very small, right? 1.155 times 10 to the negative 10. So move that decimal 10 times, yikes, really small number. Okay, so in terms of hypothesis testing, right, if you have a really small p-value, then your observation is way out in the tail, assuming the null hypothesis is true, right? And so that means it's really unlikely. So it's more likely that some other hypothesis is true, right? And so then we have enough evidence to reject H0 in favor of HA. So here it's saying, well, here's the alternative hypothesis that you gave me. The true mean is not equal to 10. That checks out. That matches what we wanted to do. So then my confidence interval, my 95% confidence interval is from 17.92, let's say, to 22.26 miles per gallon. And then the mean of X, we're told, is 20.09. So once we have our interval, we need to interpret the interval, and then we need to use it to answer the question. So I use this standard blurb and it'll work every time. And so I recommend that you use this standard blurb. So we're 95% confident that the interval from 17.92 miles per gallon to 22.26 miles per gallon captures the true mean fuel economy of all cars. Remember, we said, okay, assume this is a sample that's representative of all cars. That's not true, but that was an assumption that we made. So we've interpreted the interval, that's good. So now we can look at this interval from 17 to 22. 10 is not inside this interval, right? So we have enough evidence to conclude that the mean fuel economy is significantly different from 10. It's going to be really important that you say different, because we did a two-sided test. And so we can't conclude anything about the less than or greater than, because that's not the test that we ran. Okay, and so it's really important that you just say different. Okay, and because a confidence interval can only tell you if there's a difference. Okay. So that's if we have a mean. So that's for quantitative or numerical data. So now if I have categorical data, right, then I would build a confidence interval. So for a proportion. So if I have a one sample proportion, then I can use the prop.test command. Now, that link that I showed you, he goes through and he shows you how to build up the different components. You don't have to use the t.test and the prop.test commands. They just make it easier, I think, but you don't have to. Okay. So the prop.test takes an x, okay, where x is, so what I'll do here is I'll do another little bullet here where x, oops, is the number of successes. Okay, so whatever you want to talk about, x is the number of successes. So notice how it doesn't refer to any data. We just need the number of successes. So sometimes you have to do a little bit of work to get there. N is the sample size. P is, the hypothesized value. Okay, so P naught. And then the alternative is two-sided, that's the same, and the confidence level is 0.95. I think you could probably reverse those orders, and maybe I should do that, because otherwise it doesn't quite match. Hope it works. I'll try it once we get there, see if it works. But the confidence level, conf.level, oops, sets the confidence level. That's pretty obvious again. And the alternative needs to be two-sided to generate a confidence interval. Okay. So we're testing if there's a difference. So n/ne, if you're in LaTeX, is the not equal to sign. Okay. So what we want to know, maybe, if we're talking about a mean, right, is there evidence to support the statement that, oh, sorry, a mean, I said a mean, proportion. Is there evidence to support the statement that 30% of cars are four-cylinder cars? Use the empty cars data as your sample. Again, assume it is representative of all cars. That's not true, but that's okay. Use a 95% confidence interval to support your claim. So first thing I want to do, especially when I'm working with proportions, is I just want to check the conditions. Can I apply the normal distribution here? And so the main concern here is that I need to have at least, so this textbook says 5, but if you want to use 10, 10 is kind of is what we use typically. So this textbook has brought it down to 5. I don't really care which way, as long as you're checking it. So use 5 if you want to, or 10 if you want to be safe, right? But you want to make sure that you have at least 10 successes and at least 10 failures in your data set, okay? And so if I look at the number of cars with 4 cylinders, that's a success in this case, right? And so I have 11 successes out of 32, okay? And so we see there are 11 observed successes and 21 observed failures. So we assume the sample was randomly selected, and therefore observations are independent. We can therefore proceed constructing the confidence interval, right? You have to check these conditions before you go ahead and check your hypotheses or build a confidence interval for proportions. Now, we should have done the same thing for the mean, but pretty well, as soon as you have a large enough sample, so a sample of size 32, the central limit theorem is going to kick in and it's not going to make a difference. So we can always assume we have a normal distribution pretty well, as long as we have a large enough sample size. So 32 is large enough, so that's good. Maybe I should add that in here. We have a sample size of 32. So the central limit theorem applies, and we can assume a normal distribution. Distribution for the mean. And so maybe I should say, we assume the sample was randomly selected. That is an assumption I'm making. Okay. That was just for the mean. Figured I should check the conditions for that as well. Okay, so if we look at the empty cars $ cylinder, so that's how we pull out just one column, the cylinder column for the empty cars data set. And so we have 11 successes, 21 failures, so the assumptions are met. So then from that table, and there are way fancier ways of doing this, but I'm just going to say x equals 11. So x is the number of successes, n is my sample size, right, is 32, and my p is going to be 0.3 because I want to know if there's evidence to support the statement that 30% of cars are 4-cylinder cars, right? So the value that I want to compare my sample proportion to is 0.3. So that's what I have to put here, 0.30. You could do 0.3 if you want, but I just think it looks cleaner with a 0 after. So then if I use my prop.test, if I've defined x and n and p, then I can just refer to them generically here. And that way I could go back and I can change my x and my n and my p, and I don't have to go through and change every single line of code that I have. But you could just as well have these hard-coded, okay? So what I wanted to do, well, I first have to run these x, n, and p. So notice how they're showing up over here. Right now they're stored as those values. And so what I could do, I'm going to copy here. Because remember that change that I made and I wasn't sure, I'm pretty sure it can handle it. Just changing the order there. It works. Okay. So then I don't need this. Right. But I will say, or if you don't want to assign the values to variables, you can hard code them, but it makes it difficult to make changes later on if you have to, right? So what I mean by that is, let's keep the same setup here. I think. Make a space, make it look nicer. So what I could do is I could have 11 here. I could have 32 here. Whoops. Just want some spaces to make it look nicer. 0.30. Not like that though. Like that. Okay, so notice how if these values changed, you would have to go through and make changes. Oh, sorry, I just saw in the chat here. So as the sample size increases, the confidence interval, the width of the confidence interval decreases. And that's because the standard error is dividing by n in both cases, right? So both for the mean and for the proportions, the standard error is divided, it includes a denominator of n. So as you increase your sample size, then what's going to happen to the overall number? I'm dividing by a larger number, so the overall number becomes smaller, right? So it just means that my margin of error, so those bounds that I have, become tighter and tighter around that sample estimate, or the point estimate, if you prefer. Which is also going to lead us to the problem with big data, right? So if you have sample sizes in the millions, then you can imagine that's going to wreak some havoc, right? You're going to have really, really tight confidence intervals, which is good and bad. Okay. Now let's see here. So once we have our, hopefully okay, nice. Hopefully I answered that. Okay, so if I have a look at the one sample proportions test with a continuity correction, you can ignore that, you can change that, but I'm just going to leave it as a default, so that's fine. So it gives us a chi-squared, if you remember chi-squareds, or hang tight for stat 230. We'll talk about chi-squareds. But it's just a test statistic, right? And so the p-value is 0.7285. That's really large. So that means that we're not going to be able to reject H0. That's fine. And so the alternative hypothesis is that the true proportion is not equal to 0.3, right? And so we didn't have evidence to support that, because our interval is between 19.17% or 19.2. I went to 2 decimal places, doesn't really matter. 0.5322, so 53.2%. And then we have our sample estimate for the sample proportion, which is 0.34375. So what we found is that we're 95% confident that the interval from 19.2% to 53.2% captures the true percentage of 4-cylinder cars. Okay, we're assuming that we're able to talk about all cars based off of the sample. Thinking about the 30%, right? Since 30% is contained in this interval, it is somewhere between 19.2 and 53.2. We can support the statement that the percentage of 4-cylinder cars is not significantly different from 30. Okay. Great. Okay, so I'm going to save this. I want to knit it just to make sure that I'm not setting you guys up and it won't knit later. But I also want to show you the LaTeX in action. So remember how we had, I'll zoom in here. Okay, how can I make this larger? Wow, just wants to be huge. Okay, so, and like I said, this is mostly an excerpt from that link that I posted. So you have that on a Moodle, but I also posted it here just for a quick reference. But notice when I use those $ and those /mus and the /nes, right? That's how I'm able to generate this nice looking text, okay? And so, oh, my trackpad batteries are low. It's annoying. And so, so that's just something that you might want to keep in mind, right? If you are using it maybe for the assignment 6, okay, or the assignment for chapter 6, I should call it. And we know that it produces all the output here. You could suppress it and only call out the important information, but in this case, it's okay to have all this kind of nasty looking stuff included in your report. That's okay. You could try using cable, but I'm not sure it'll work to make it look nicer. Maybe, I haven't tried. Okay, good. So I think that's all I wanted to show you for the R code, and that should be all the R code that you need that's new, that you might not have seen before for the assignment for chapter 6. Okay, so how do I stop sharing this? Okay, and we're back here. I'm going to close R because otherwise it tends to slow things down here. Close this. All right, now go back here, share this screen. I'm all over the place here. Maybe in a good way, who knows? Organize this here, the chat. Okay. Okay, so, right, I don't really know what to do for review, but I did say I wanted to put in the notes the due dates. And so the first presentation, and maybe I'll put it down here. We said was due November, and I'll say it's on the Wednesday, November 10th, of course, at 11:59. Okay, and then the assignment for chapter 5, the assignment for chapter 6, and the second presentation, oops. Oh, that doesn't look good. I can never do the right-hand side curly bracket. Can do a left one just fine, but not a right one ever. Oh, well, I'll try again. Close enough. They're due Friday, November 19th at 11:59. Remember, the second presentation, I'll clean that up. I'm not sure it got any cleaner. Yeah, so you have to submit your report, but I'm only marking the presentation, but I do want to see the report and I'll still read it. And I might, give 1 mark just for submitting it or something like that. But the majority of your marks are just for the presentation. Okay. But I want to see the report and then I want to see the presentation. Oh yeah. Hey, good. Forgot about the quiz. We're going to have quiz 3. And what I want to do is I want to open it because we don't have classes the 11th or the 12th, but I'm kind of strapped for time. So what I decided to do is kind of rude, I know, but I want to open the quiz Wednesday night and have it open till the Sunday night. Okay, so quiz number 3 will open November 10th after class, potentially before, but kind of, let's say after class for now until I decide if we have enough time to give you time during the class, but I'll just say after class. And close Sunday, November 14th. Yeah. And so you'll have lots of time to do it. It's a 50-minute timed quiz. From the lecture material, I'll say that. From the theory material, because that means that there's no R code or anything like that, right? And so just from the theory material in class. Okay. Okay. Do you need to submit any written work for the quiz, or? Quiz 3 is for, let's see here, chapter 6 and 7. For the quiz, no. You don't have to submit any written work. I haven't had you do that for any of the quizzes, right? I don't think so. No, it's just theory material. So you're good. Okay, I think that's good. That's a lot. Let's see here. Any other due dates that we should talk about? It's probably good. Okay. So when we do a hypothesis test specifically, then when we make a decision to reject the null hypothesis or fail to reject the null hypothesis, there's always a chance that we're wrong, right? And so when we conduct a hypothesis test, and conclude that we can reject the null hypothesis or fail to reject the null hypothesis, And we conclude, oops. We can, or we have enough evidence, let's say, we have enough evidence to reject H naught, or do not have enough evidence to reject H naught, right? There's always a chance, there's always some chance that we are making the wrong decision, right? There is always some chance that we are making the wrong decision. Oops. The wrong decision. Okay. And so what we do is we call those type 1 and type 2 errors. Okay. So the two types of errors we could make are type 1 or type 2 errors. Yeah. And maybe I should capitalize the type here. So we've got this table, which I find really useful. So, oops, sorry. Usually I have to kind of set up a table like this in my mind, or just kind of have it handy so I can remember which one is which, a type 1 error and a type 2 error. So for example, if the conclusion that you've made is that you do not have enough evidence to reject H naught, okay, if the null hypothesis is true, then that's fine. You're good to go, right? That's the correct conclusion. Whereas if in reality the alternative hypothesis is true, we call that a type 2 error. Okay, so that's when you don't have enough evidence to reject H naught when it should be rejected, right? And so here, I'll scoot this over. And if HA is true, H naught should be rejected. Okay. Whereas if H naught is true, then it shouldn't be rejected. Okay. So if we should have rejected H naught and we didn't have enough evidence to do that, then that would be a type 2 error. Okay. Typically, we can control the type 2 error rate mostly by increasing our sample size. Okay. Whereas if we reject H naught and H naught is actually true, then we made a type 1 error. Okay. Whereas if we rejected it when it should be rejected, that's the correct conclusion, right? And so a type 1 error, and I wonder if I can just bump this up. I just need 2 lines. Type 1 is basically if you send an innocent person to jail, right? And a type 2 is, so I guess we haven't been using this. You know what? Let's just talk about how to control it. So a type 1 error, the type 1 error rate, let's say, is the significance level or once you have a p-value, it'll be the p-value, but the error rate is the significance level, or the alpha level. So we can adjust it, because if you remember, for hypothesis testing, you go into it with some significance level in mind. Typically the default is 0.05, right? But if you want to adjust the type 1 error rate, you could increase it to 0.1 or you could decrease it to 0.01, depending on the severity of your conclusion, right? What's the severity of making a type 1 error? Okay. Oops, period. The default alpha level is alpha equal to 0.05, but we can adjust it. To 0.01 or 0.10, right? Depending on the severity of rejecting H0 when it shouldn't be rejected. Depending on the severity of rejecting H0 when it shouldn't be rejected. When it shouldn't be rejected. Okay. So that's how we adjust for the type 1 error rate. We can say, okay, I'm okay with potentially making a mistake 5% of the time, 0.05. That's the default. But if you're okay with making that mistake 10% of the time, what does that tell you about the severity here of rejecting H0? Well, it means it's not that big of a deal, right? It means that maybe you're making a conclusion like this cereal is significantly cheaper than this cereal, right? It's not going to make or break anything, right? Whereas if you are doing a test and rejecting H0, right, is going to cost you a lot of money, right? Then you want to be really, really sure that you're not rejecting H0 when it shouldn't be rejected. Okay, so then you would lower your significance level. Whereas the type 2 error rate can only be controlled by increasing the sample size, right? Because the type 2 error is when you don't have enough evidence to reject H0 when it should be rejected, right? So in truth, there is a difference there. There is a significant difference, but you're just not able to detect it. Probably because, as we were talking about, the standard error is so large that your bounds get so wide that even though it should be nice and tight around the point estimate, right, you're still capturing that that hypothesized proportion or mean when it shouldn't actually be in the interval anymore, because we need to increase our sample size so we get a better estimate. So the type 2 error rate can only really be controlled, and I shouldn't say only because there are other tools, but for us, it can be controlled by increasing the sample size. By increasing the sample size, which decreases the standard error and the margin of error, which are those bounds, especially in a confidence interval, which is probably the easiest thing to think about, and the margin of error around the point estimate. Okay. Good. It's a lot about type 1, type 2 errors, but they're really important, right? We have to keep in mind that we could always be making a mistake, right? And so, so that's why it's really important that we don't say that we accept a hypothesis. For example, we can never accept a hypothesis, and I'm sure I've said it before, but I'll say it again, right? And so since there is always a chance our conclusion is wrong. Oh, hello. Oh, question? Maybe not. I don't see anyone. Okay. So since there's always a chance our conclusion is wrong, we can never accept a hypothesis. Okay, so our only options are we have enough evidence to reject H0. We're not saying that we accept it. We're just saying, or that we accept HA. We're just saying, okay, well, I have enough evidence to say that's not it, right? That doesn't mean that the alternative hypothesis is correct, right? There's a chance that I'm wrong, right? Or I don't have enough evidence to reject H0. I'm not saying that I accept H0 because there's a chance that I should be rejecting it, but I'm not, right? So our only options are we have enough evidence. Oops. We have enough evidence to reject H0, or we do not have enough evidence to reject H0. If you have enough evidence to reject H0, usually we follow it up by saying in favor of HA, right? But really at its core, right, we either do or we don't have enough evidence to reject H0, and that's it. Okay. So we've talked about all of this, all of this type 1, type 2 errors, and here there is a quick review of the steps for hypothesis testing, which you should have a really good overview either from Stat 230, or you will have a really good overview from Stat 230. But here it is, a quick summary, so that's good. You don't have to do a formal hypothesis test on the assignment, so you're fine, but it's nice to have here, especially for quiz questions, that kind of thing, right? So but obviously, if we haven't covered something in Stat 230, then it's not going to be on the quiz, because that just doesn't seem fair. So, but if you're not in my Stat 230, it's assumed that you already have a stats course. So, so then all this should just be review. Okay. So here I included the hypothesis testing summary. This is using Excel. And that's really good if you just want to check your answers and you want to get quick values. And I showed you how to do it in R as well. So you've got many tools. So here it's important to note that we've only talked about procedures for testing hypotheses about the mean or one proportion, right, for a single population, right? And so, of course, we could extend that. We could talk about comparing 2 samples, comparing 3 samples, comparing 4 samples, right? And so we can also test things that are not the mean or the proportion. We can test other things, okay? And so there are lots of other things that we could do but this is a pretty good overview of some of the core things that we might want to do. Okay, so we want to wrap up and just talk a little bit about big data specifically, and things like practical significance versus statistical significance. Okay, so the problem, or it's not really a problem. It's just our current tools don't really adjust for when we have big data, right? And so what we know is, as we increase our sample size, right, then our interval, let's talk about confidence intervals, then our interval around the estimate becomes super, super, super small, right? And so then we're basically just hanging out at the estimate as we increase our sample size. And so here, I encourage you to read all this, right? I've summarized it for a reason. But there's things like sampling error versus non-sampling error. So sampling error is just deviations from the population that would just happen naturally by collecting a sample size that's less than the population, right? Whereas non-sampling error can come from a variety of places, right? Coverage error, non-response error, measurement error, right? All those things would increase the error of your estimate, right? And so here, you've got a couple notes on sampling. Also, these should all be review, right? And so, I'm going to skip ahead here. So big data, we can talk about the 4 V's of big data, right? And so there's volume, right? The amount of data. That's typically what we think about when we talk about big data, right? There's the variety, right? So the diversity in types and structures of the data that we're looking at, right? Maybe we've got this like kind of unwieldy mishmash of different types of data sets and different just data types in general, right? Veracity is the reliability of the data generated, right? Maybe it's unreliable data that you're getting in masses, right? And then velocity, so how quickly are you generating new data, right? Google is generating data all the time. Oh, I hope she didn't listen. She didn't say anything. Right, and so you're constantly generating new data. So these 4 put together are all parts of big data, right? So big data is kind of this umbrella term that we talk about, but usually we're talking about huge volumes, right? So we can have tall data. Whoops. Tall data is, okay, so you've got all your observations and they're basically, in a long column like this, or you can have wide data where you've got an observation and then you've got all the different variable points. So how you store your data, that's going to matter because the analyses that you do depend on how you've stored your data. Now you're going to be able to massage your data and kind of move it around to be something that you need. But overall, the key part about big data is the precision of confidence intervals. Okay, and so here, this is the part that I want to talk about. So we've seen that we can use confidence intervals, right, to make inferences about the population parameters, whether that be the proportion or the mean, it doesn't matter, right? And so, but the validity of any interval estimate depends on the quality of the data used to develop the interval estimate. That's fair, right? And so no matter how large the sample is, if the sample is not representative of the population, then that's a problem, right? Then we can't talk about that population. Right? And so one thing is big data, you need to be really, really precise about the population that you want to analyze. we need to be exact about the population we want to analyze. Right? So that could include just extracting a portion of this big data. You would still have big data. You would still have lots and lots of data points. Let's put it here. Okay. So when we're talking about confidence intervals, right? So we're really talking about some point estimate, so the sample mean, and then we build with a margin of error, which is our critical value, T alpha over 2 if you prefer, or I just call it a critical value, times the standard error of X bar if we're talking about a mean. So for example, here, last year, the mean time spent by all visitors to penningtondailytimes.com was 84 seconds. Okay, so they want to analyze, of course, you know, has there been a change since last year or since 4 years ago? It doesn't matter. Suppose that PDT wants to assess whether the population mean time has changed since last year. Oh, surprise, surprise. PDT now collects a new sample of 1 million visitors. That's big data, right? To its website and calculates the sample mean time spent by these visitors is 84.1 seconds. Okay. So then the estimated population standard deviation, which is estimated by the sample standard deviation, is 20 seconds. Okay, so the standard error, which is S over root n, is 0.02. Okay, and so of course now at 1 million we have a sample size that's large enough so we can assume we have a normally distributed mean. So the 95% confidence interval for the population mean is 84.1 plus minus 0.0392. So here, check it out. We've got this interval from 84.060810 up to 84.13920. Okay, it's really, really, really close. This is a very, very small interval, right? So here, very tight interval, I'll say. Okay. So if we were to go about this as we normally would, right, then if we know that last year they spent 84 seconds on the website, right? So then now we want to compare our sample mean of 84.1 seconds. Is that significantly different from 84, right? And so if we had to, we could set up our null and alternative hypotheses. So our null hypothesis is that mu equals 84, and the alternative hypothesis is that mu is not equal to 84. Because the not equal to is what I need if I'm testing with a confidence interval. Okay. So then now we have this interval here. What we'll say, first I'll interpret the interval. Interpret the interval. We are 95% confident the interval from 84. Now, I don't want to be rounding because, right, I'm going to lose a lot of information. So I'm going to keep all these decimal places. Maybe I'll keep 3 decimal places because I want to make sure that I see enough of a difference, right? So 84.061 seconds to 84.139 seconds captures the true mean time spent on the website this year. Oops. This year. Now, when I look and I take my 84, my hypothesized mean of 84, it's not in this interval, right? We can look at it like this, right? And so I've got my interval from 84.061 up to 84.139. And of course, my sample mean of 84.1 is in there, right? But my hypothesized mean is over here, 84, right? And so since my hypothesized mean of 84 is not contained in the interval, I have enough evidence to reject H0. Okay. So since the hypothesized value of 84 is not contained in the interval, we have enough evidence to reject H0. Oops, evidence to reject H0. Since I'm rejecting it, I'm going to say in favor of HA. This means that, what does this mean? The 84.061 to 84.139, that's our interval for this year, right? So the mean viewing time or the mean time spent on the website is statistically significantly different from last year. Okay. So this means the mean time spent on the website this year is significantly different, right? Statistically significantly different. Usually we just say significantly, and it's implied that, of course, we did a test, is statistically is significantly different. We can only say different because we did an interval, right? So the interval can only tell us if there's a difference, right? Because our alternative hypothesis was that the mean was not equal to 84, right? And so this means the mean time spent on the website this year is significantly different from last year. Okay. That's all good. The problem is 84.1 seconds versus 84 seconds. They may be statistically significantly different, but not practically significant, right? And so that's where this big data comes in, and we need to take a step back and say, okay, well, was there a practical difference here? Because we're able to basically detect statistical significance wherever we go, because we have these huge data sets that make our interval around our estimate so small that as soon as our estimate, our sample mean, for example, is even slightly different from the hypothesized mean, we're going to be able to reject H naught, even if they're really, really close like this, right? But we need to stay on top of it and say, well, this isn't necessarily practically significant, right? Because we can't apply this. We can't use this because a difference of 0.1 seconds is not practically significant. Okay. We notice that a difference of 0.1 seconds may not be, I don't know if that's practically significant. I'm just guessing it's not, right? And so, so we notice that a difference of 0.1 seconds may not be practically significant. So I'm going to highlight the statistically significant versus the practically significant. Okay. Just make sure I didn't forget anything. Same thing for the p-values, right? Just as we saw with that confidence interval. So here it goes on again. And but what we're getting at is that, okay, we're going to get a statistically significant result. And so you just need to be aware of if it's practically significant. Okay. I think that's good. We'll start chapter 7 on Friday. It's potentially a review on regression or a quick intro to regression if you're in Stat 230. So of course, if you're in Stat 230, we're going to go through it in more detail, but this will provide a good overview. Okay, if you have any questions, let me know. Otherwise, I'll see you on Friday. Stop this.